Now, let me deal with objections that might be raised against this premise. And here I want to get to David's point, that it is very, very often said that subatomic physics or quantum physics is a counterexample to this first principle. That the physics of the subatomic realm, quantum physics, shows an exception to this first principle. Because on the subatomic realm, certain types of particles, like virtual particles, can come into being for a fleeting moment out of the quantum vacuum, which is this sort of sea of energy that underlies all of reality. And spontaneously, these particles can come into being, and then they almost immediately vanish back into the vacuum again. And sometimes people have tried to apply quantum physics to the origin of the universe and say, well, maybe the universe is just a fluctuation out of nothingness. And sometimes you'll hear these almost rhetorical expressions like, nothingness is unstable, or the universe is a free lunch because we got something for nothing, or the universe is a quantum fluctuation out of nothingness, and so forth. But I think that this objection is based on misunderstandings. In the first place, and this is the number one point, not all physicists agree that the quantum realm is causally indeterminate. That is to say, not all quantum physicists believe that the quantum realm, the subatomic realm, is not causally determined. The indeterministic interpretation of quantum physics is under the so-called Copenhagen interpretation, which is the interpretation of the father of quantum mechanics, Niels Bohr, Danish physicist. And on the Copenhagen interpretation of quantum physics, it's true that these particles are said to arise spontaneously out of the vacuum without any sufficient determining cause. However, you need to understand, and most people don't understand, that the Copenhagen interpretation is just one of many different interpretations of quantum physics. In other words, any scientific theory has a mathematical core, and then it has a physical interpretation of the mathematics. And quantum mechanics has the same mathematical core, but it has at least 10 different physical interpretations that I can think of, at least 10. And not all of these 10 are indeterministic. For example, David Bohm has an interpretation of quantum mechanics which is fully deterministic. On this view, the uncertainty is purely mental. You may not be able to determine what is the cause of the origin of some quantum event, but it does have a cause. And Bohm's theories are mathematically consistent. They are entirely consistent with the evidence. There's no way evidentially to distinguish between the Copenhagen and the Bohmian interpretation, and yet the Bohmian interpretation is fully deterministic. So when people tell you that quantum mechanics furnishes a counterexample to the premise one, all you have to do is simply point out that that is not a proven counterexample, because there are lots of interpretations of quantum physics that are fully deterministic, and so this is not a proven exception to premise one. But secondly, second point I want to make, even on this Copenhagen interpretation, these particles do not come into being out of nothing. They don't come into being out of nothing. The quantum vacuum is not what the layman thinks of when you say the word vacuum, namely nothing. The quantum vacuum is a sea of fluctuating energy. It is an arena of violent activity, and it is governed by physical laws. So it is far from nothing. And what happens is, on the Copenhagen interpretation, that this energy locked up in the vacuum fluctuates and can spontaneously, for a brief time, spin off particles that then dissolve back into the energy of the vacuum. so that they do not come into being out of nothing, as would be the case with the origin of the universe. Take the question in a second. I want to make a third point, though. The third point is that on interpretations of the origin of the universe, in which the universe comes into being out of the vacuum, the same point holds. Namely, they do not talk about the universe coming into being out of nothing. As we'll see later when we get down to 2.34, the vacuum fluctuation theory, they are talking about a sea of fluctuating energy out of which the universe originates as a vacuum fluctuation. So it is not creation from nothing. So when you read in popular magazine articles and newspapers that the universe is a free lunch because it came out of nothing, or that nothingness is unstable to fluctuations, this is just a misuse of language. These are rhetorical flourishes that are not taken seriously by scientists and philosophers. Nothingness, when you think about it, can't have any properties because it isn't anything. To say that nothingness is unstable or has properties is to treat it as though it were something. And so nothingness can't have any properties because it just isn't anything. So it can't have instability or anything of that sort. So we'll talk more about these models later on, but I think this is enough to say why quantum physics doesn't furnish a counterexample to premise one. Let me just quote from a philosopher of science named Robert Deltet. This is what he says by way of summary. There is no basis in ordinary quantum theory for the claim that the universe itself is uncaused, much less for the claim that it sprang into being uncaused from literally nothing. All right. Now, was there any comment on that? David, did you want to comment on that? Or
I think your second point, that this quantum vacuum is really not the same as nothing, is an excellent one. I think it's easy for lay people to get mixed up about that, but you're right on the line. I would say your first point about other interpretations, most folks do buy into this Copenhagen interpretation right now. It may change in the future, but that's pretty much what people are thinking.
Yeah, I certainly agree with you that this is the traditional view, but I think that that may just sort of be the contemporary paradigm, but it isn't to say that it's therefore, well, it's certainly not empirically better than Bohm's because they're empirically equivalent, so it's a matter of taste in a sense. All right, any other comment or question on this first premise? Yes, Kathy.
Is there an argument there about the fact that these things that pop out of nothing can't sustain themselves, they disappear? Is that...
Well, this is a good point. I mean, in the quantum vacuum, when you have, like, as David said, a positron and an electron coming into being, they can't stay in being longer than something called the Heisenberg indeterminacy principle allows, because then you would violate physics. So they have to dissolve back into the vacuum in a real hurry, or it's going to upset the scientific apple cart. So these particles are sort of able to hide, in a sense, in this period of scientific ignorance. And I think that's why Bohm's view is plausible to say that this uncertainty is just in our heads. It's not necessarily in reality.